All right, on to the next part of the class. So now we're going to go over proof of work. This is my favorite part of the class. Proof of work is this concept that's been around since the early 90s. And when I like to explain proof of work, I like to think about what it was initially created for. Proof of work was tossed around as this concept of making it more computationally expensive to send an email, right? Because when you had physical mail required that you go down to the post office. It required that you get, a stamp. It required that you get the ink to print the letter on and then send it to somebody. It was pretty difficult to send a piece of mail. And then if you wanted to send 1,000,000 pieces of mail, it was going to be, you would have to set up a real operation. I mean, maybe you would automate a lot of that away and you wouldn't necessarily drive down to the post office, but it'd be difficult. The average person wouldn't be able to just send 1,000,000 letters to people, even if you had their addresses, right? So similarly for email, we want to make it so that it's going to be difficult for people to do email spamming. So we're going to do like proof of work for email spamming. So you want to make it so anyone could send an email to their friend over here, right? So we say, yeah, we're going to let that happen. Anyone can send one piece of mail to their friend, and that should be pretty easy, right? Email has opened a lot of doors for us. It's made it really easy for us to communicate across the world. So we want to keep it easy to send a piece of email to someone across the world. So what we do want to stop is someone from sending millions of emails, right? So if this is 1,000,000 emails, and we're sending all of these all over, our nice green planet here. Lots of little land masses. Oh man, this is not a good planet. Am I going to try to draw it in? Oh, it looks like a Yoshi egg. Okay, well that's supposed to be the Earth, right? So we're basically trying to prevent this. We're going to say no. We don't want to be able to send millions of emails all over the world, or at least we want to make it difficult for a spammer to be able to do that. So conceptually, we could add a price to each email so that if it costs a penny to send email to your friend, then it will cost 1,000,000 pennies, $10,000 to be able to send 1,000,000 emails to people. That's one way of doing it. So, it's not your average person with a modern internet connection and a modern computer can't just send 1,000,000 emails, right? You have to have a bit of an operation. Another way to do that is to make it computationally expensive to do it. So hang with me for a second here. What if we could make each piece of email require 60 seconds of computation time, right? For the average user, that's not going to be really noticeable. Maybe you can even run that in the background. So like you send the email and then it takes 60 seconds to go through. Your friend gets it in a minute and a few seconds, right? The email goes through pretty fast as far as they're concerned. For 1,000,000 emails, if it's costing 60 seconds of computation time, that's going to be, times 60 seconds is going to be 60 million seconds per email, for all the emails, right? Which is going to be what, 1,000,000 minutes, which is roughly like 20,000 hours. Which is going to boil down to maybe multiple years of work, of computation time, right? A few years of computation time. So your email spammer could scale this up by putting multiple CPUs. They could, run this computation across multiple CPUs, across multiple computers, and kind of scale up this operation. It works very similarly to adding a price to something, but your price, the work that you're actually putting in, is the computation time, right? So that's very important. That's a very important concept. The proof of work is that it does create an actual price in electricity, especially when you scale up the numbers, right? Because it takes a certain amount of electricity to be able to run these computations. It's computationally expensive. Okay, so how does that work? right? If we were going to want to do something like that, right? It all sounded pretty magical. That might make it a little bit more difficult to run spamming. How are we going to implement that? So what we want to do is we want to make it so you need to create some work for every email that you send, and then you need to prove to the network that you've done that work, right? All right. So the first thing that we're going to need to do is we're going to need to uniquely identify every email. And that's so that we can actually create a specific proof for every email as well. So hang with me here. Remember, this is all about proof of work in emails. So to uniquely identify an email, maybe we take a couple different pieces of information, right? We're going to take the address, who we're going to send this to. We're going to take the contents of the email. And we're also going to take a timestamp, right? Because you could be sending the same contents to the same person at a different time, and that we want to make that a unique email, right? So we're going to take these three things, and we're going to hash them together. Remember, we talked about the hash function earlier. It's a one-way function that will create essentially a random value for us, right? Some value that, without having hashed all of these items before, we wouldn't know what that value is going to look like, not even roughly, right? It's completely random to us. So if we pass this through our little SHA-256 function, it's going to output something like 0xFA23, some 64 character long hexadecimal string. That's just the first 4 characters there. Cool. So that works. We're hashing together all these contents. We haven't accomplished anything yet. This is pretty easy. Running one SHA-256 algorithm doesn't take very long for a computer to do that. Maybe a couple seconds. So what we want to be able to do is we want to make it difficult to send this email. So we're going to establish some kind of rule to make this a little bit more difficult. So one of those rules is we can actually make this hash, the first 4 digits, we can require that they be 0. If we do this, then the rest of the hash can, still be whatever random values, FAB7, ... But what's going to happen here is we already know what the address and the contents and the timestamp come out to be. What we're going to need to do to come up with something that has 4 zeros as the first 4 hexadecimal characters, we're going to have to start tossing in some other random value in here. Maybe it's 1, maybe it's 14, maybe it's 147, right? This random number we're going to refer to, in Bitcoin, you're going to see this as the nonce, right? Basically, you're going to take this number, randomly hash it together with the other things to come up with something that satisfies this condition down here of the 4 zeros being in front. And we can scale this 4 zeros. It doesn't have to be 4 zeros, it could be 1s, or Fs or dead beef, whatever you want to put in there, because it's hexadecimal characters, right? Zeros just happens to make it easy. That's how Bitcoin does it. And you can scale it up according to how hard you want to make it, right? Because the more zeros you put in front, the more rare it's going to be to do that, right? That first 0, if it's 1 bit, a bit being 0 or 1, in order to get one that starts with 1 0, that would be 50% of the time the first one's going to start with 0, right? And then 50%, and then 25% of the time, that second one's going to start with 0 also, right? You kind of see how it's going to exponentially become harder to come up with the zeros as you go down. It's an important aspect. So you can kind of scale up the level of difficulty as you want to make it more difficult for bigger hashes. All right, so how does this relate to Bitcoin? Let's get back to Bitcoin, right? So in Bitcoin, I'm going to put it up here, Bitcoin proof of work. So in Bitcoin, we have this concept of mining, right? It's the idea that you want to control the emissions rate of how often a Bitcoin gets minted. Bitcoin has a very specific schedule for how often it wants to be minted to the network, and there's a certain amount of Bitcoins that will ever be mined, right? So let's first draw out this little Bitcoin, and we'll put a B, and we'll put those little fancy, yeah, look at that. And then we'll make a miner, or we'll try to. Let's see. He's got a little pick. No, it's not bad. Okay. So he's going to try to mine that, mine that Bitcoin there. And essentially, so now we need to look at the emissions rate of Bitcoin, right? So Bitcoin initially started with the first reward for a Bitcoin when it was mined was worth 50 Bitcoins. So that was back in 2009 when Bitcoin started. Every time that a block was mined, it would be a reward of 50 Bitcoins to that particular miner. And this would happen every 10 minutes. So we have a 10-minute block time. This is the reward. And this is our block time. So in the beginning, every 10 minutes, 50 Bitcoins were mined. After 4 years, there was a halvening, right? Every 4 years there's a halvening, which means that the reward is getting split in half until eventually there will be no reward. But it started with 50, it went to 25, 12.5, and then every 4 years it's going to go down, right? It's going to half. So what we want to do is we want to encourage, the whole idea behind the reward for Bitcoin mining is to encourage more nodes to be in the network, because that adds to the security of the network. That creates more decentralization to have more people in the network. So initially, there were only a couple computers mining Bitcoin, right? There was initially just Satoshi's computer mining, and then, Hal Finney came along, and then maybe a couple more cypherpunks, like more and more people started joining in here. This is really what we want, right? We want a bunch of people joining in the network. That's good. But as the network gets bigger and bigger, it's going to be easier and easier to find the next block, right? Because you have a ton of machines all trying to come up with the next block. So you have a lot more power, right? You have a lot more ability to come up with a hash that might be tougher, rarer to come up with. So what you do is you scale up that difficulty, right? So maybe we started with the 0x0, and maybe we just made the first 2 characters have to be zeros. And then maybe we made the third one. Since this is hexadecimal, each hexadecimal character is represented by 4 bits, right? So we could also, it doesn't have to be a hexadecimal character that's a 0, but you kind of get what I'm saying here, right? You can essentially scale up the difficulty as you go along. So as the hash power gets bigger, we're going to make that more difficult for somebody to push it out there. And essentially, so this idea of proof of work, the idea is the work is the hashing. All that time that the computer is going around trying to take the nonce and randomly come up with a value, right? In Bitcoin, it's taking the data, it's taking a timestamp, and it's taking a nonce, and it's trying to calculate a hash that satisfies whatever this rule is, the difficulty. And we can basically control what that difficulty is. We're not going to know what that hash is. There could be many hashes that satisfy this, with different nonces. But eventually someone will find it, and then they'll be able to mine it to the network and get paid for it. That's essentially how proof of work works. So now we're going to dive into some coding exercises. These coding exercises are meant for you to kind of solidify the concepts that we just went through and be able to apply them. So this is your chance to go ahead and try to apply the concepts we learned, and I'll be here in case you need any help. So let's go ahead and dive into those code exercises. Pull up the IDE. Now it's your turn. We're going to add to our blockchain, we're going to add this proof of work mechanism.